Welcome! This video will be about waves. More specifically, we set out to derive a partial differential equation called the wave equation that describes the motion of small amplitude waves through a stretched rope. Interestingly, it turns out that the wave equation can be applied in many other physical contexts as well. You can think about the motion of water surfaces, as in the background picture, but also acoustic waves, seismic waves, vibrating strings, and many more. And the fact that the same PDE turns up in so many physical contexts is quite remarkable if you consider the many different mechanisms at play. After all, the physics of vibrating strings and water waves is very different, yet they are described by the same equation. Let's derive that equation. And while we'll derive it, I strongly suggest you pause the video when needed and take some notes along the way. Here are Alice and Bob. They want to understand the mathematics of waves and decide to conduct an experiment using a rope. Alice and Bob, they hold the rope on both ends and keep it stretched tightly, pulling it with a force Ft in opposite directions. Suddenly, Alice decides to shake the rope while maintaining the tension. As a result, a short wave is excited, which quickly propagates from Alice towards Bob. And now the question Alice and Bob would like to answer is how to mathematically model this wave. Well, to this end, they decide to zoom in and take a closer look at some small segment of the rope, that is. The rope traces out a curve which can be described using horizontal and vertical coordinates x and u. The segment has a length of delta x and a mass of delta m, which is proportional to its length. Now, what forces are causing the rope to move? Newton's second law of motion tells us that the mass times the acceleration must be equal to the applied external force. Now let's assume, for simplicity, that the only force acting on the rope is the tension caused by Alice and Bob's pull. On the left end of this tension is a force F1 with magnitude Ft pointing in the direction of the rope, and similarly, on the right hand side there's a force F2 with magnitude Ft. Theta 1 and theta 2 measure the angles between the force vectors and the horizontal direction. The total force acting on the entire segment is then simply the sum of F1 and F2. In this case, that's a downward pointing force. Now, Alice and Bob make an important simplification. They assume that the angles theta 1 and theta 2 are going to be very small, which effectively means that the wave amplitude u will also be very small. How does this assumption simplify our analysis? Look at the picture. We have decomposed the force vectors F1 and F2 into horizontal and vertical components. For starters, it's not hard to see that for very small theta, F1 and F2 will be nearly horizontal. And because the magnitude of F1 and F2 are both equal to the tension Ft, we find that the horizontal components cancel each other. As a consequence, the total force acting on the segment must be purely vertical. Well, now that we know the force must be vertical, can we also find its magnitude? Sure. It turns out that the vertical components of F1 and F2 are related to the slope of the curve, which is du dx, at both ends. I want you to pause the video here and show yourself that the following relations are true. Did you succeed? Finally, we combine both vertical components to obtain an expression for the total force acting on the rope segment in terms of the derivatives of u. We do now have all ingredients for the wave equation. But first, let's go back to Newton's second law. We have shown that for small wave amplitudes, the total force is purely vertical. According to Newton's law, the acceleration must then also be purely vertical and equal to the second derivative of u with respect to time. Using this, Newton's law becomes this. The second ingredient is our expression for the vertical component of the total force. Substituting this on the right-hand side gives us this. Note that Newton's law starts to look like a partial differential equation now. The third ingredient is our expression for mass. Recall that the mass is equal to delta x times the mass density rho, and if we divide both sides of the equation by the mass, we get this. But at the surface, this equation looks very messy. But take a closer look. Do you recognize the rightmost fraction? Indeed, it looks familiar. If we take the limit where x approaches 0, then this fraction is exactly the derivative of du dx with respect to x. So in fact, it's a second derivative. And finally, we arrive at our wave equation. That's it for now. Well, almost. Remember that the wave equation should describe many different sorts of waves, like water waves, acoustic waves, seismic waves, etc. Well, the general version of the equation is this one, and it happens to describe all of them. Also, it turns out that the constant a is the propagation speed of the wave, but let's stop here, okay? You will learn more about wave equation in class. See you there.